Alright, hello and welcome to part 2 of my tutorial series on Matlab's Numerical Ordinary Differential Equation Solver. As I said, this video will include two-dimensional examples. Now I decided to split this part up into a couple of videos just to keep things better organized and in the interest of time. So in this video I'll be introducing the basic process very quickly, and I'll still be doing a two-dimensional example. And then at the end of this video, I'll also be talking about how these examples can relate to examples with higher dimensionality or higher degrees of freedom. We will still, of course, run our example through Matlab. In another video, I'm just going to include another physical example with 2 dimensions because I love physical examples. I haven't decided how complicated that example is going to be yet, but we'll see when we get there. So, let's go ahead and deal with this first part here. Now, you'll see that when we talk about how to handle these problems with, 2 dimensions, that the process really isn't different at all from the one-dimensional process. It's just a matter of now including multiple functions and those multiple functions derivatives in our state vector. But outside of that, the process is pretty much the same. So when we're dealing with ODE45 or whichever other ODE solver you're using, we're still going to have 3 inputs, and those inputs are still going to be the derivative of our state vector in terms of time and the state variables, the time span, and the initial conditions. The time span and the initial conditions will always be easy to obtain. You'll be given these in some kind of problem statement, or alternatively, you will already know these values because you might be trying to test out some system and see what different parameters will do with that system, how the system will respond to those. Most of the effort is really in getting the derivative of your state vector, which requires us to know our state vector itself, but getting that state vector, as we saw last time, isn't really that much of a hassle. So let's go ahead and deal with this guy when we're talking about 2 dimensions. So when we're in 2 dimensions, our state vector is still going to be a vector consisting of state variables, S1 all the way down to Sn. And now these state variables will include the functions, plural, that we're solving for, and their respective derivatives all the way down to the I or j minus 1th derivative. So let's say that we're solving for functions x and y. Then our state variables will represent x and x dot all the way down to the I minus 1th derivative of x. And it will also include y and y dot all the way down to the j minus 1th derivative of y. And the reason you'll see me using I and j here is that I want to make it clear that the highest order derivative of x is not necessarily the highest order derivative of y. So let me kind of show that through a physical example. If I have x double dot plus x dot plus x equals 0, and I also have y dot plus y equals 0, then in the system of differential equations, the highest order derivative of x is 2, so I is equal to 2. But the highest order derivative for y is just 1, so j is equal to 1. For the case when you run into problems like these, when the highest order derivative for one function is not the same as that for another, I just decided to distinguish between I and j. You can run into these kinds of problems. Now if you're wondering what the size of our state vector is going to be, it's just going to be I plus j. So n is equal to I plus j, which in this case is equal to 3 for this problem. So if we were to approach this problem and get our state vector and try to go from there to get the derivative of our state vector, then we would have 3 state variables, S1, S2, and S3. And from our definition that we have over here, we see that these guys will just be x, x dot and y. Likewise, the derivative of our state vector is going to be very easy to get. We're just going to have x dot, x double dot, and y dot. Again, MATLAB wants the derivative of our state vector in terms of our state variables. We already see that x dot is s2, so we can write that in. But we still have the highest order derivatives for x and y. And just like before, our job is going to be to express the highest order derivative, or really the highest order derivatives, in terms of the lower order terms. In this case, x double dot is very clearly negative x dot minus x, and y dot is very clearly negative y. If we were to express those terms in terms of state variables, that gives us y dot is equal to negative s3, i.e. negative y, and x double dot is equal to negative s2 minus s1, i.e. negative x dot minus x. And we still have s2 on the top. And now we have a format that is suitable for MATLAB. So again, as you can see, this process is pretty much exactly the same as for the one-dimensional process. It's just a matter of including other functions as opposed to just one function in our state vector when we're talking about our state variables. Now I just want to point out that sometimes, perhaps oftentimes, you will run into equations that are coupled. And if you've never heard that term before, when I say coupled, or when someone else says coupled, they mean that one of the functions depends on another. So in this system of differential equations, there's a sense in which x depends on y, and there's also a sense in which y depends on x consequently. But that's okay. The process for solving this system is still going to be the same. The highest order derivative for x is 1 in this instance, so I is equal to 1. Likewise, the highest order derivative for y in this instance is 1, so j is equal to 1. And that tells us that n is equal to 2. So our state vector is going to have two components, s1 and s2. And these components, again from our definition earlier, will just be x and y. Now this equation is extremely easy to solve, so getting s dot is pretty simple also. We have x dot and y dot, and if we were to solve for these guys, x dot is just equal to negative y, which would be negative s2. Whoops, there we go. And y dot is just equal to negative x, which is negative s1. And once again, we have a format that's suitable for MATLAB. You might find it strange that there's a sense in which the highest order derivative of x is expressed in terms of not only, x and its derivatives, but also y and some of its derivatives. And the same goes for the highest order derivative for y in terms of x. But that's okay, it'll happen sometimes. The important thing is that you're correctly expressing the highest order derivatives in terms of state variables. As long as you do that, MATLAB can handle your problem. With all that being said, let's go ahead and jump into a simple example. So let's say we have x double dot minus y dot equals t squared, and we have x dot plus y dot minus 4x minus y is equal to 0. And we have initial conditions, x of 0 equals 0, x dot of 0 equals 0, and y of 0 equals 1. This tells us that our initial time is going to be 0. And let's look at what happens until a final time of 10 seconds. So all this holds our initial conditions and our time span. all we need to do is get the derivative of our state vector. Looking here, we see that the highest order derivative for x is 2, so I is 2. The highest order derivative for y is 1, so j is 1. And so the size of our state vector is going to be 3. So our state vector is going to include 3 state variables. We have S1, S2, S3. And following our definitions, that gives us x, x dot, and y here. Likewise, S dot is going to be x dot, x double dot, and y dot. This is similar to the problem we had earlier, just a bit more complicated. So you will be seeing some repeat here. And x dot is just S2. Again, we have to get the highest order derivative in terms of the lower order terms, so we can express them as state variables. I'm going to work with this second equation here first, because it'll give me y dot right off the bat. So y dot, looking here, is just going to be equal to negative x dot plus 4x plus y. And we can substitute this guy into this equation up here. So for the top equation, and I'm just going to circle this so we keep this in mind. For the top equation, we have x double dot equals t squared plus y dot, and that's just going to be equal to t squared minus x dot plus 4x plus y. So that's x double dot. And now all we have to do is toss these guys into our derivative of our state vector in terms of state variables. I'm going to scroll down a bit to give us some more room. So if I were to write out s dot, that would give me negative x dot plus 4x plus y on the bottom, t squared minus x dot plus 4x plus y in the middle, and just S2 on the top. And expressing these guys as state variables, that gives us negative S2 plus 4S1 plus S3 on the bottom. In the middle, it gives us t squared minus S2 plus, okay, there we go, plus 4S1 plus S3 in the middle there, and then we just have S2 on the top. And this is the derivative of our state vector in terms of time and the state variables. So that's really all there is to it. As you can see, there's not much of a difference, as I said earlier, between the one-dimensional problems. It's very easy to do still. Let's go ahead and toss this into MATLAB now. So we're here in the MATLAB environment. Again, I don't want to bore you guys by writing out the code for each of the individual methods that I talked about in the previous video. So I'm going to show the code for 2 of them, and I'm going to write out the code for the last one. So here is the code for what I call the M-file method, which is the code for what most of you guys will probably be familiar with, given the way people on YouTube or the way that professors even teach people how to use ODE45 and other Matlab ODE functions. Here's the code for the function method. And you can pause the video as you need to you know, just get a clear picture of the code and write it out yourself or whatever. And then over here, I'll be writing the code for the function handle method. So let's go ahead and write that out. I'm going to declare a function, as with before, and it's going to give me the time, x, x dot, and y. Because now we have 3 state variables, right, that we're working with, as opposed to in the previous video when we only had 2 state variables that we were working with. So these are the outputs for this function that I'm going to make. I'm going to call it practice 3 2D. And let's get started. So for the time span, or actually what I'll do is I'll go ahead and declare the variables first. So x naught is 0, x dot naught is 0, y naught is 1. We have t naught being 0, and we have t final being 10. And I will comment that as values. So here are all the initial values that we were given. Now I will declare the time span. It is just t naught, tf. And I'll declare the initial conditions in a vector as well, which will just be x naught, x dot naught, and y naught. Now I'll declare s dot as some general function of time in the state variables. Again, going off what we had earlier, what we wrote earlier, for the first line we were just going to have s2. For the second line we are going to have t squared minus s2 plus 4 times s1 plus s3. And for this last line we're going to have negative s2 plus 4 times s1 plus s3. So there's our s dot. Let me make sure that's correct from what I have over here. Yep, looks the same, looks safe. Okay, cool. So now we can go ahead and call ODE45. So I'll have time and state values equals ODE45. S dot is the function that's giving me S dot. The time span, the initial conditions, suppress the output, and then I'm just going to go ahead and extract those values. So I'm going to comment this code as well. Call ODE45 solver, and then extract individual values. So x is going to be equal to column 1 in our state values matrix. X dot is going to be equal to column 2, and y is going to be equal to column 3. Again, we explained this process and why the outputs work this way in the previous video. So I'm going to extract these values, and then I'm also going to plot x of t and y of t. So I'll call figure 1, I'll clear the figure, and then I'll plot time versus the x values, and I'll title that the same thing I titled it earlier in the other codes that I wrote over here. And then I'll pull up figure 2, clear the figure, and plot time versus y. And title it numerical y of t. That should be it, so I'll end this function here. I will save it. Boom. And then I'll call it down here in the command window. That was very fast. Okay, well, here are the solutions. As you can see, they don't look too different. Pay special attention to the axes, right? Here is a times 10 to the 7th. Here's 16 times 10 to the 7th. So these two plots are not the exact same plot, even though they may look similar in shape and size. So here are the solutions for x of t and y of t. I don't really care to plot x dot. You can do that if you want to. But that's it. That's it for the MATLAB portion, and I'll make some final comments before closing out the video. Okay, so I just wanted to point out a few things before closing out because I think they answered some important questions. This first one is really going to be the most important. And that's just the question of what are you going to do when you're dealing with more dimensions or more degrees of freedom? And I'm using those terms interchangeably because when you're solving these differential equations and putting them into MATLAB, the problem's going to come out and be approached the same way. But in any case, what are you going to do with more dimensions? And really, there isn't much of a difference between what we did in this video and handling more dimensions or more degrees of freedom, right? So I don't need to toss out an example with, say, a 10-degree of freedom system with all these complicated aspects. Just as there wasn't much of a difference between one-dimensional problems and two-dimensional problems, so there isn't that much of a difference between two-dimensional problems and problems that have even more dimensions. For instance, if I have a three-dimensional system, so I have 3 dimensions, I have 3 differential equations, right? And I want to have my state vector. Okay, my state vector is still going to be a vector with n state variables, right? S1 to Sn. And these state variables are still going to represent the functions that we're solving for and their derivatives up to their respective I or j or k minus 1th derivative. So let's say we're solving for functions x and y and z. Then these state variables would represent x and its derivatives all the way down to the I minus 1th derivative of x. And y and its derivatives all the way down to the j minus 1th derivative of y. And finally, also z and its derivatives all the way down to the k minus 1th derivative of z. Where again, I'm using different letters to point out the fact that the highest order derivative for one function may not necessarily be the highest order for another function. But that should already be obvious here. And then if we want to know the size of our state vector, it's just going to be I plus j plus k. And again, the process will be the same. We'll still be trying to get the highest order derivatives for all of our functions in terms of the lower order terms so that we can express them as state variables when we're getting our derivative of our state vector, because MATLAB wants it as some general function of time and the state variables. So the process is the same, it's just longer and more drawn out, and the same goes for more dimensions or more degrees of freedom, right? So there's no need to jump into, say, a 10-degree of freedom example and some crazy vibrations problem, because it'll just be so much longer handling all of this with 10 degrees of freedom, 10 functions to deal with, and it takes up too much time. So just be aware that this relates to higher and higher and higher dimensional systems. Same process, you can do it, it'll just take longer. The second thing that I wanted to point out, and these last two things are kind of smaller things, is that when people are writing out their state vectors with multiple dimensions, they might do it slightly differently. So what you saw me do was you saw me kind of write all the derivatives for x first, in the first portion, and then you saw me tackle the y portion, right, when I was writing out the state vector. Now, some people prefer to kind of alternate between x and y or whichever other functions they're dealing with. So someone else might write this instead as, x and y, and then x dot and y dot, and then x double dot and y double dot, so on and so forth, right? From what I've seen, it doesn't matter which one you choose. MATLAB is so capable of giving you a correct answer as long as you program your code correctly. I like to do it this way because it just, helps me have x and its derivatives organized together, and then y and its derivatives organized together. Whichever way is easiest for you, just stick to that. But both work just fine with MATLAB. And the last thing that I wanted to say was just to be prepared to do a lot of substitution when you're running into problems that have more and more degrees of freedom or higher and higher dimensions. You saw what happens when you have these differential equations and the highest order derivatives for the functions appear in more than one equation. So for instance, in the example we had earlier, we had y dot, which was the highest order derivative for y, and it appeared in both of the equations that we had. So we had to get y dot, and then we had to substitute that into the earlier equation, and that was just for a two-dimensional system. If you have more dimensions or more degrees of freedom, there's just that much more forwards and backwards substitution that you're going to have to do. Don't let it tire you out. You can do it. There is a solution. It'll just be, again, longer to deal with. But that's all the comments that I have. So that pretty much sums up and ends this video. So I hope that all this information was helpful. Again, let me know down in the comments below. Was it helpful? Was there anything that I can do to improve this? Are there any examples that need to be shown? And thanks for watching, and good luck in your MATLAB ventures.